Hello everybody. Let us talk about density operators for pure and mixed states. We early characterized quantum systems using state vectors called kets. We have already described this concept of state vectors, which are known as kets, and how we can use the kets to represent the quantum systems. But now let us consider an alternative way, which is an equivalent way to the representation of the quantum systems. This is called density operators. The density operator, and is also known as the density matrix, is a fundamental concept in quantum computing and quantum mechanics. Now, this density operator helps us to provide a complete description of the quantum system, especially when the system is in a mixed state rather than a pure state. So, when the system is in a mixed state, density operators are very useful to represent the systems, because in that case state vectors won't be able to represent the system. If the system is in a pure state, then both density operators and state vectors are helpful. But in the case of mixed state, density operators are helpful to represent the system, and the state vectors won't be able to represent the system. Before we move forward, let us discuss briefly about the pure and the mixed state. We have already covered in one of the videos, but let us briefly discuss about what is a pure state and what is a mixed state. A pure state is that state of the quantum system in which the state of the system is perfectly known. In quantum mechanics, full knowledge of the state has a probabilistic dimension. For example, imagine we have an observable A with eigenvalue equation written as A ket ui equal to lambda subscript I ket ui. Here the subscript I is important because the subscript I will traverse through all the eigenvalues of this operator A. And let us say that the quantum system is in this state ket psi, and ket psi we know that is given by the quantum superposition of the eigenstates, where Ci's are the expansion coefficients, which are complex numbers, and Ci's are given by the projection of psi onto the eigenbases. So this is also known as the representation of ket psi in U basis. We have already discussed these concepts. So we also know that the probability of getting the measurement outcome which will be one of the eigenvalues. So probability of the eigenvalue lambda I will be given by magnitude squared of Ci. Ci magnitude squared, where Ci is the coefficient corresponding to the eigenvalue lambda I, and we assume that the eigenvalues are non-degenerate eigenvalues. We know that ket psi is a pure state, as this is all we can know about a quantum state. So when the system is in this ket psi, it is a superposition state, and this is a pure state because the state is not mixed. And what do I mean by that? There is no statistical probability playing role in the overall probability scenario. And what is statistical probability? When the knowledge of the system, when we have partial knowledge of the system, or we lack in the overall knowledge of the system, then in that case the system representation will involve the statistical mixture of states. That means the statistical probability will play a role in that case. But when we have perfect knowledge of the system, in that case the state of the system is a pure state, because the system the representation of the system will involve only the quantum mechanical probability. So quantum mechanics tells precisely how to determine coefficient Ci at any given time, and then how to calculate its time evolution using the Schrödinger wave equation. So we will be able to, using quantum mechanics, we will be able to find out the coefficient Ci, and we will use in that case the Schrödinger wave equation for exploring the time evolution, and we will come to know the final minimum energy state in that case. Now, what is a mixed state? When the state of the system is known partially. To describe a system, if we have incomplete information about the system, this is a feature that exists in classical world. We have probability concept in the classical world. So the probability is used in the classical world because we have partial knowledge of the system, and then we use probability to say that with this probability certain event will happen. But if we have the full complete information about the state, then we don't need this statistical probability. Then only the quantum mechanical probability will exist and not statistical probability. But if the state is a mixed state, in that case the probability will come from two directions. One will be from the quantum mechanical world and the second will be from the classical world, which is basically the statistical mixture of the states. The probability, that probability will be known as the statistical probability. So this is a feature that exists in the classical world, and this is unrelated to the probabilistic nature of the pure states in quantum mechanics. In mixed state, we have partial information in the sense that the quantum state can be in any one of the following states: ket psi 1, ket psi 2, ket psi n, with these probabilities, and the sum of the probabilities will be equal to 1. Whereas in the case of pure state, the system will be in only ket psi state, not like ket psi 1, ket psi 2 and ket psi n. So that is why we say that we have partial knowledge about the system when the state is mixed, and we have the full knowledge about the system when we have the pure state. That means we know that the state of the system is ket psi. We have no ambiguity that the state of the system is either ket psi 1 or ket psi 2 or ket psi n. Now each of these states are pure states. Individually these are pure states and each has a quantum mechanical probability associated with it. But the point of mixed state is that we don't know in which of these pure states our system is in. This is precisely where the probabilities P1, P2 and Pn come into play. These probabilities are independent of the quantum mechanical behavior, and these probabilities exist in the classical world also, as I have just described previously that the statistical probability exists in the classical world also. Now what is a density operator? Density operator is actually an equivalent formalism to the state vectors. A state vector ket psi only describes the pure states. Real quantum systems often interact with the environments and experience decoherence. Decoherence means the system loses the quantum superposition, because the quantum supremacy of the quantum system comes from the quantum superposition, which is responsible for quantum parallelism. But when the system interacts with the external environment, and that we call as the decoherence, and because of this decoherence the system will lose its quantum superposition and the quantum behavior, and therefore we may not be able to get this quantum advantage if the system due to decoherence will lose the quantum mechanical behavior. So in a way the system will lead to the mixed states. So density operator is necessary to describe open quantum systems, which are basically called as the ensembles, and partial tracing of these entangled state. Meaning by, what is an ensemble? Ensemble is basically the system is in the it can be in any of these states with certain probability. So how do I define the ensemble? The ensemble will be a set where the system can be in state ket psi I with the probability pi. So this will be termed as the ensemble, where when the system will be in one of the ket psi states with certain probability. To introduce the concept of density operators, let us choose the set of eigenbases. Let us introduce the concept of density operators, and for that let's consider the eigenbases represented by ket ui. I is an index that traverses the number of eigenvalues, and these are assumed to be orthonormal. These eigenbases are normalized also, and they are orthogonal to each other. So these are the eigenstates, and the inner product of ui with uj can be expressed as a Kronecker delta that explains the normalized and the orthogonal relationship. So ket psi we know that can be expressed as sigma psi sigma I Ci ui, ket ui. So density operator rho, which is represented by rho cap, is defined as the outer product of psi with itself. So this is the definition of the density operator. Density operator rho cap is basically for every operator that we use. So rho, in the subscript we have psi, because we are when the system is in state psi, then we are trying to describe the density operator. It is given by the outer product of psi with itself. So this is valid only for the pure states. Similar to the projection, this is similar to the projection operators on the state ket psi. And indeed, the projection operator and the density operators are the same. To write an operator in a particular basis, we have to calculate its matrix element, because this outer product will result into a matrix form. So therefore, we need to know all the elements of this matrix. So let us write density operator in U basis, for which we have to calculate its matrix element. We know that given an operator, I and j are given an operator. Operator is basically a matrix. So given a matrix with I index representing the row number and j index representing the column number. So this matrix elements are given by this factor, ket ui row, bra ui row and ket uj. And if we substitute the value of rho, we can express it like this. So this is Ci, this is Cj conjugate, because this is bra of psi and uj. So the matrix elements are given. So matrix elements can be calculated as the coefficient Ci multiplied the coefficient but with its conjugate. And this inner product of ui with psi is the amplitude in the basis state ui, and uj psi is the amplitude in the basis state uj. So that is basically this part. This Ci part is, which is the quantum amplitude for ket ui basis, and Cj is the quantum amplitude for the ket uj basis. That's what I am trying to explain here with this formation. So therefore, the state vector ket psi and the density operator. So now we have two equivalent representations. One is the state vector, which is ket psi, and other is the density operator, which is rho ij. So rho ij is basically equal to, that means the matrix elements are calculated like this: Ci Cj conjugate, and whereas ket psi is basically a row vector, where the row vector elements are the coefficients, like this. So this is the representation of the two equivalent counterparts for representing this quantum system. One is the state vector and the other is the density operator. Now the density operator has got certain properties. Only then the operator will qualify as the density operator. Now what are the properties? The properties are, it has to be Hermitian. That means the adjoint of the density operator should be the operator itself. So this is easily proved. So you take the outer product, take its adjoint, which will be equal to the operator itself. The density operator has to be idempotent, means the square of the density operator is the operator itself. So that can be easily proven. So this property is true for a pure state but not for mixed state. This property is true for the pure state, but we cannot prove this idempotent property for the mixed state. And there is no global phase ambiguity, because if we consider the ket psi as if the system is in state ket psi, so therefore we can write the density operator as the outer product. So if, let us say, with certain global phase we get a new quantum state which is ket psi dash. So when we try to calculate the new density operator by taking the outer product of ket psi dash with bra psi dash, so it will be equal to, so this global phase will cancel with each other and you will get the original density operator without any phase ambiguity back. And the rank of the density matrix tells us about the number of pure states involved in describing quantum system. Rank of the matrix is equal to the number of linearly independent rows or columns. For density matrix, it is equal to the number of non-zero eigenvalues. So the rank of the matrix is also equal to the number of non-zero eigenvalues. So this particular result will be helpful in the numerical problems, where we will have to prove that whether this given density matrix qualifies for density matrix or not. In that case, we will have to calculate the eigenvalues, and we will have to prove that all the eigenvalues are non-zero eigenvalues. Then we can say that this matrix or operator qualifies for the density operator. Now here are some facts about the rank of the density operator. When the rank of the density operator is 1, it leads to a pure state. System is exactly in one quantum state. When the rank is greater than 1, it will be a mixed state. That means it will be a probabilistic mixture of pure states. And when it is equal to certain factor d, which is the dimensionality of the Hilbert space, in that case that will be known as the maximally mixed state. Now let us take an example. If we have ket psi, that means the state of the quantum system given by this row vector, if we calculate the density matrix from here, it will be equal to this. Now if you look at the density matrix and if you try to calculate the eigenvalues, you will see that it will have only one non-zero eigenvalue. So therefore the rank of the matrix is 1, right? In that case, this qualifies for the density operator. Now let us take the second case in which the density matrix is given, and this has rank 2 because there are 2 eigenvalues. For this, if you calculate the eigenvalues of this matrix, you will see that you will get 2 eigenvalues. Therefore the rank is 2. So therefore it is not this is not a density operator for the pure state. Now when we have to prove for the normalization, so we are given the density operator. We can calculate the density operator by taking the outer product, and we know that the matrix elements can be calculated using the coefficients, multiplication of the two coefficients. When we take the conjugate of when we take the conjugate of one of the coefficients. Now for state vector, we know this is the normalization condition, that the inner product has to be equal to 1. So if we try to use the representation of ket psi and we try to look at the norm of this psi, in that case that will be equal to the summation of all the magnitude squared of all the coefficients. This norm will be equal to the magnitude squared of all the coefficients, and it has to be equal to 1. Now density operator of a normalized state. So therefore if the state is a normalized state, the density operator will be equal to Ci square, and this will be equal this basically represents the diagonal elements. So diagonal this result comes from here. Now if you look at this result, this is the case of a normalized state. So norm of the vector is given by this sigma mod Ci square. So therefore this is basically rho ii if we try to put it in terms of the density operator, which will be equal to mod Ci square. So this has to be equal to 1. So therefore diagonal elements of the density matrix in the U basis tells us the probability of measuring the system to be in the corresponding Ui state, right? And if we take the sigma of mod Ci square, so this has to be equal to 1. So therefore we can say that the probability of we can say that the probability of all these elements is equal to 1, right? So what are these elements of the density operator? These are the diagonal elements of the density operators. In that case, what do I mean by, if you take the sum of all the diagonal elements, that is equal to the trace. So that means if the trace of the density matrix is equal to 1, so therefore this is normalized. So this is another condition. This is the condition of normalization in terms of the density operator, that the trace of the density operator has to be equal to 1. So therefore we can write the normalization condition using the state vector as the bracket of the state vector, which is equal to 1 of course, with itself, and also the trace of the density operator is equal. These expressions are equivalent. Now, a quantum system is fully specified by the expectation value of a complete set of commuting observables. So that means we know that what is the expectation value of a certain operator A. It is given by this brass I A cats I. To convert it into U basis, insert. So if you want to convert it into U basis, let us insert two identity operators like this, because inserting the identity operators will not change the result, because multiplying any operator by the identity operator, we get the same operator. So therefore, and we can also replace this I with this outer product in both the cases, right? So that we introduce the ui basis here and uj basis here. And if we do the manipulation, we will see that this expectation value will come out to be ci conjugate, cj, aij, and the summation. So in terms of the density operator, we can write the in terms of the expectation value, we can write the expectation value can be written in terms of the density operator like this. So this is equal to uj rho a and uj. So that means what I'm trying to prove here, I'm trying to calculate the expectation value of this operator A, but I want to put I want to calculate I should calculate the expectation value using the density operator. Now if you do the manipulation of a little bit of mathematics here, and you will result into this result, which is equal to uj rho a uj. So this is putting expectation value in terms of the density operator here. Now suppose the system is in a pure state cat psi, and the density operator is given by the outer product of psi. Measure the observable in un basis. So if you measure this observable, if you measure any observable in the un basis, the probability of obtaining outcome un is given by the Born rule. If we want to obtain the outcome un, so that means the corresponding probability of the eigenvalue will be given by this Born's equation, Born's rule. And if we use this right hand side of the equation, which is the probability of the eigenvalue, and we do certain manipulation, so we will be able to put the probability equal to in terms of the density operator. Now since rho and u, the outer product of un, so both these are operators. This is also operator, and this is also, rho is also operator. So we can write probability of lambda n, which is the probability of an eigenvalue, is equal to the trace of rho with the outer product of the eigen basis un. And this eigen basis, this outer product of un will be written as trace of rho pi n. Pi n is given by this. So that means we can express the probability in terms of the density operator also. So projection operator corresponding to the measurement outcome. This comes from the true identity of the trace. So trace of the two operators can be written like this: sigma j, j basis, a b j basis. And that's what exactly is done here when we have this expression. This is equal to two operators which are un with un are two operators, and rho is another operator. So two operators are there, and we are trying to calculate the trace. So once we are trying to calculate the trace, so these two expressions are equivalent expressions, right? So this is let me just okay, actually this expression will be used here. This is the expression where when we try to calculate the expectation value, we can prove it equal to this sigma j and uj with two operators. Now if this expression is there, then we can use the trace identity to put it in terms of this expression, which is trace of rho and this pi n. Pi n is this outer product of un. We basically use this trace identity to solve. I express expectation value in terms of this expression. Now I use the trace identity to put this expression in terms of the trace expression, which is given by trace of this. Right. In the case of mixed states, now consider the statistical mixture of states psi k with pk probabilities and such that all the probabilities will lead, summation of all the probabilities will be equal to 1. So let us have some observable A with eigenvalue equation given by this. In mixed states, it turns out that it is more convenient to work with density operator. Density operator is more useful because in all the above derived formulas for pure states, the density operator density operator appeared in a linear manner. If you look at the density operator here, let me explain this point. The density operator appeared in a linear manner, whereas the state vector can appear in the quadratic manner. How? When we do the when we try to calculate the expectation value using the density operator. So density operator appears only one time, whereas when we do the when we try to calculate the expectation value using the state vectors will come 2 times. So therefore, I say that the density operator appeared in a linear manner, whereas the state vectors can appear in a quadratic manner. While doing certain calculations, especially for calculating the expectation value, I am trying to show that the density operator appears linearly in the expression, whereas the state vectors appear in a quadratic manner in the calculation of the expectation value. Thank you very much.